So if you know anything about cards, how many cards are in a deck of cards? 52, okay? How many of them are kings? 4, okay. So what I want to do is I want to determine the probability that if I pick 3 cards from a deck of cards, all 3 of them will be kings, okay? But I'm going to calculate it in 2 different ways. The first way, we're going to replace the first card before we pick a second, and then replace the second card before we pick a third, okay? The second way we're going to compute this is we're not going to replace. And we're going to see if we get the same probability or a different probability. What do you think? Do you think with and without replacement will produce the same probability or different probabilities? Different, okay? We'll see. So, if we're doing it with replacement, the likelihood that the first card I pick is a king is going to be equal to what? 4 out of 52, okay? The likelihood that the second card I pick is a king is going to be equal to what? And how about the third card? So if I want the first card and the second card and the third card to be kings, what do I do with those 3 fractions? Multiply, okay? So I did that, okay? I took 4 out of 52 times 4 out of 52 times 4 out of 52, and I got 0.0039. There it is, okay? Okay? Now, what's going to be different in our calculation if we don't replace the cards as we pick them? The first probability is 4 out of 52. What's the second probability if I don't put the first card back? 3 out of 51, because there's only 3 kings left out of 51 cards left, right? And then how about the third card? What's its probability? 2 out of 50. So I've adjusted for the fact that they're not independent by adjusting my fractions. So if I want to find the probability that the first, second, and third cards are all kings, I can multiply these, okay? Because I've made an adjustment for the fact that they weren't independent, and that was by reducing the number of kings and reducing the number of cards in the deck, right? Okay. When I calculated this, I got a different probability. We were right. In fact, this probability is like 3 times, almost 3 times more likely than is this, which should make sense because, of course, every time I pick, I've got more kings in the deck to pick from, okay? All right, so when we're picking cards and we replace or don't replace them, we get different probabilities of getting all 3 of them to be kings, okay? But now let's look at this next example, okay? The next example, let's say we've got a pool of juries, a pool of jurors to select from, okay? 12,000 different people that we can pick to serve on a jury, okay? And let's say that it's known that 3,000 of them are women. And we want to know the probability that if we pick 3 jurors, all 3 of them will be women, okay? Now, in this situation, let's figure it out. First, by replacing the first juror we pick and then replacing the second juror, okay? What's the probability? Oh. Sorry. I'm dying. I feel like okay. What's the probability? The first person I pick is going to be a woman. 3,000 out of 12,000, okay? If I put her back, what's the probability of the second person I pick is a woman? The same. And the third, right? Okay. So if I'm picking 4 jurors, say, the probability that all of them will be women, if I replace them, now I'm crying, is equal to 1/4 times 1/4 times 1/4 times 1/4, right? Okay. So I calculated that. And I got that to be equal to 0.0039. Okay? Now, in reality, do you put the person back before you pick a second juror? No, because the same person can't serve on the same jury twice. So we really, in reality, would not sample with replacement, but rather without. So the chance the first I pick is a woman is 3,000 out of 12,000, right? What's the chance the second one is a woman if I don't put the first one back? Yep, say it louder. Yep. And now you keep going down by one. One fewer woman, one fewer total juror, right? Okay, so I calculated that. Here's the probability the first is a woman. Here's the probability the second is a woman, the third and the fourth. When I multiplied those together, I got 0.0039. What do you notice? They're pretty much the same. Their next digit was different, but they're almost exactly the same. Why? What's that? Why did it not matter if I replaced the woman or not? Bailey? It's so large that removing one person from that large group doesn't have a very noticeable impact, if any impact, on the probability, okay? So I'm taking a very small sample from a really large sample space, as Bailey said, and therefore not replacing that person or those people doesn't have a noticeable impact on the probability that all four of them will be women. So in situations like this, where we're working with such a large sample space, you can assume that even without replacement, your events are independent, and you can just multiply 1/4 times 1/4 times 1/4 times 1/4 and get a very, very, very close approximation of the true probability that it would be without replacement. Make sense? Any questions about that?